I'm going to get started. I wanted to begin just with the reminder about test number 2 that's coming up next week, and it's in our Thursday lecture class. So you'll sign on to Zoom as usual for the Thursday lecture class, and you'll take the test through Canvas as we did through test 1. It's going to have the same basic types of problems, the multiple choice, numerical answer, and the long, fully worked out problem. Although I'm going to change a bit the point scheme so that the long worked out problem that has partial credit is worth a bit more, and the numerical answer questions that were worth 10 points each will be worth somewhat less. The material that we're covering is the material since test 1. So that's the material on energy and work, chapter 5. It's the material on impulse and momentum, that's chapter 6. Those are the great conservation laws that describe the motion of matter. And then it's this new material we're working on now, which is going to be a combination of circular motion and universal gravity. And it's a combination of circular motion and universal gravity because we need circular motion to understand universal gravity. So that's why those two topics are joined together. Okay. Let me switch on the chat again. And let me get started with today's lecture then. Okay, so we're continuing from Tuesday's class on circular motion. We're going to continue with circular motion on this class. And on Tuesday's class, basically we explored how to describe circular motion like we had previously explored how to describe linear straight line motion. So in linear straight line motion, we use displacement, velocity, acceleration to describe the motion. And we met some equations of motion that apply to constant acceleration motion. In circular motion, in a similar fashion, we introduced angular displacement, angular velocity, angular acceleration to describe circular motion. And we met the equations of circular motion that apply to constant angular acceleration circular motion. So that's really a summary of what we did last class. It's a quick recap of all we did last class. What we're going to do this class is kind of what we did early on in the semester. After describing kinematics of straight line motion, we moved on to the dynamics of straight line motion, the explanation of straight line motion. So after we've now described the kinematics of rotational motion, introduced the description of rotational motion, we're going to move on to the dynamics of rotational motion and explain why things rotate. So earlier on in the semester, we moved on to dynamics for linear motion and talked about forces and acceleration. And now we're going to move on from kinematics of circular motion and talk more about forces and acceleration in context of circular motion. But I gotta do this problem that I didn't get to at the end of last class. I want to go back to this James Bond problem. I want to go back to it because I wanted to cover an example of tangential velocity, tangential acceleration, and how they're linked to angular velocity, angular acceleration. But in this problem is a puzzle that leads us into dynamics, leads us into our understanding of circular motion, leads us into our explanation of circular motion. So we've got to cover this one. Anyway, if you remember, in Moonraker, James Bond unfortunately got fooled into sitting in a centrifuge, and they tried to kill him in the centrifuge. And this problem is about his little trip in the centrifuge, and we're told that James starts from rest. He accelerates at 0.1 radians per second squared, and he rotates for 5 complete turns. And after that duration of his rotational motion, we got to figure out his tangential velocity, his tangential acceleration. So let's go ahead and do that. There's one more piece of information we're given here, that the centrifuge was 10 meters in radius. Okay, so as you know, I always draw a diagram before working on a problem. And so here's the diagram. It's a simple little one. In blue is the centrifuge, and James is in it somewhere over here, maybe. And he's rotating counterclockwise in my sketch. And I've written down the things that I know and don't know about his rotational motion. Because the way I'm going to solve this problem, to find the tangential velocity and the tangential acceleration at the end of the duration of James Bond's trip in the centrifuge, I'm actually going to first use my rotational kinematics to figure out the angular velocity at the end of his trip in the centrifuge. So let's do that. We know he starts from rest. We know his angular acceleration was 0.1 radians per second squared. And we know his journey lasted for 5 complete turns, 5 revolutions, or multiplying by 2 pi, 31 radians. And when we work with our equations of circular motion, we're always going to be working in radians for angular displacements, angular velocities, angular accelerations. Okay. So now we've got to calculate the angular velocity. So let me try and do that. And here we are. That was quick. I went back to my equations of circular motion that I actually remember by remembering the equations of translational, straight line, linear motion, and then just rewriting them in the language of rotation with, thetas and omegas and alphas for the displacements, the velocities and accelerations. And this equation here, this one I've written down, it's going to work for me. It contains the initial angular velocity, which was 0. It contains the angular acceleration and the angular displacement, which we know. And so I can use this first equation to figure out an equation for the quantity that I want, the final angular velocity. And actually, all I've got to do, if this first piece is 0, it's easy. I just need to take the square root of the left and right-hand sides. So I get this equation here, and all I got to do is fill in the angular acceleration, the angular displacement, 0.1 radians per second squared, 31 radians, take the square root of that stuff, and I get the answer. His final angular velocity is 2.5 radians per second. And that's what I need to go on and calculate the tangential velocity of James. So let's do that on the next slide. Let me clear all this. And here we are on the next slide. I'm going to work out now those two quantities that we were asked for. Tangential velocity and tangential acceleration. And let's go ahead and do that. So firstly, tangential velocity. That's this little guy here. Now, we're pretty careful. We tend to be careful about writing tangential velocity as v subscript t. It is the velocity of James tangent to the circular motion that he's executing. And so we're careful about saying this is the tangential velocity around the circular path. And all we need to do to calculate that is multiply the angular velocity of the rotational motion by the radius of the circle. And so that's all I did here. Angular velocity was 2.5 radians per second, and the radius of the circle was 10 meters. So we get 25 meters per second. That's his tangential velocity, tangential speed that after those 5 turns in the centrifuge. Now we got to do the tangential acceleration. So let's do that. And since that was easier, again, we're careful in indicating that this is the tangential acceleration. It's the acceleration around the circle that's tangent to the circle. It describes whether the circular motion is speeding up or slowing down. And to get that tangential acceleration from the rotational motion, from the angular acceleration here, all we have to do again is multiply by the radius of the circle. And we were even told the angular acceleration in the problem. So I'm just going to multiply by 10 meters that angular acceleration, and I get the answer 1 meters per second squared. And so that's the calculation of these tangential velocities accelerations from the original rotational angular velocities and accelerations. And so it's an example of that bridge, that link between rotational quantities describing the motion of the centrifuge as a whole, as like one body that's rotating, and then the tangential velocity, tangential acceleration is describing, the motion of a point on that body. That point was James Bond here. We're describing how James Bond himself is moving in meters per second and meters per second squared. Okay, let's clear that. Let's move on. Oh, Brad Pitt came to the first class, but I haven't seen Brad Pitt since the first class. But now suddenly we're talking about Moonraker and a movie, Brad Pitt shows up for class. So anyway, I'm a little disappointed with him, but he has an interesting question. When we saw the movie, James Bond passed out. And Brad is asking, well, look, you've just calculated the tangential acceleration. It's 1 meters per second squared. The acceleration of gravity, that's 9.8 meters per second squared. So James Bond's tangential acceleration is only 10% of the acceleration of gravity. So why would he pass out for such a small acceleration? So that's a very interesting question. And the answer is that tangential acceleration is not the only acceleration that's lurking in, that's beneath the circular motion of James Bond in the centrifuge, or beneath any circular motion of anything moving in a circle. There's actually another acceleration, we call it centripetal acceleration, and we denote it A with a subscript C, and there's a corresponding force with it that we call the centripetal force, F with a subscript C. And so this leads us into centripetal acceleration, centripetal force, and these are the reasons. These accelerations, the centripetal accelerations, the centripetal force, is why James Bond passed out in centrifuge. Okay, so as we analyze centripetal acceleration, centripetal force in circular motion, I'm going to think about a special case of what we call uniform circular motion, is constant speed circular motion. We're not going to worry about circular motion in which something speeds up, rotates faster, something slows down, rotates slower. We're just going to first focus on this special case of uniform circular motion. So this is the case where I meant angular, well, I knew I was going to do that sooner or later. This is a case where angular acceleration is 0 and angular velocity is constant. That's uniform circular motion. It's when there's no speeding up, no slowing down. It's also a case, right, when tangential acceleration is going to be 0 because the angular acceleration is 0. And tangential velocity is going to be 0 because the angular velocity is 0. Again, that's because there's no slowing, no speeding up, and no slowing down. So it is a special case, but it's a very important special case. And we're going to look at this special case just to keep things a bit simpler as we begin to investigate this world, this kind of hidden world, I think of it, of centripetal acceleration and centripetal force. Okay, so just to stress that whilst uniform circular motion is a special case of circular motion, it is a very important case of circular motion. Here's some familiar examples to you of circular motion that is actually uniform circular motion. So the rotation of the Earth over here on the left-hand side of this slide, that's uniform circular motion. That's circular motion at constant angular velocity with 0 angular acceleration. Motion of the Earth around the sun. That's also uniform circular motion. It's motion, the Earth is constant angular velocity. It has 0 angular acceleration. And then finally over here, another one you're familiar with, the motion of the moon around the Earth. Likewise, that's uniform circular motion. That moon has constant angular velocity and 0 angular acceleration. And all of these are super important, right? From ancient times. This is how we tell the time of the day. This one's how we tell the season of the year. And this also was, full moons and new moons. They're how we would distinguish months, how we define months. So they've all been important in measuring times on different time scales, from times within a day to times across a year. Okay, so this slide, the goal of this slide, importance of this slide is that we want to recognize that even in uniform circular motion with constant angular velocity and 0 angular acceleration, there actually is acceleration and forces. So this is a sketch here of the Earth's orbit around the sun. Obviously, it's not to scale, right? The Earth in this is bigger than the sun. And the distance between the sun and the Earth is the same sort of scale as the size of the sun and the Earth. Obviously, it's nothing like that, but it does show us the Earth moving around the sun. On the little sketch, I've drawn the velocity vector, the linear velocity vector, meters per second, that the Earth is traveling at several different locations. You could imagine there in the summer, in the fall, in the winter, and in the spring, at these 4 locations. Downstairs here at the bottom, right? Oh, didn't mean to do that, but that's okay. The Earth is traveling in its circular orbit and is traveling at that moment from the left to the right of the slide. Over here on the right, the Earth is traveling from the bottom to the top of the slide. Over here upstairs, the Earth is now traveling, this is a half a year later from where we started, is traveling from the right to the left. And then finally this picture here, the Earth is now traveling from the top of the slide down to the bottom of the slide. So the Earth, when I drew those velocity vectors, I tried to draw them, but although not perfectly, their lengths are the same. The Earth is covering the same number of meters per second in the spring, in the summer, in the fall, and in the winter. But the direction of the motion is changing. And if the direction of the velocity is changing, just as if the magnitude of velocity is changing, if the direction of velocity is changing, then there's acceleration. And so looking at this picture, thinking about this picture, it makes it clear that since the velocity is changing because the direction is changing, there is an acceleration of the Earth in its motion around the sun. And that acceleration is what we call centripetal acceleration. So this is a realization that there is a thing called centripetal acceleration when you have uniform circular motion, like the Earth around the sun, like the moon around the Earth. Okay. In this slide, I want us to figure out the direction of that centripetal acceleration. And in the next slide, I want us to figure out the size of that centripetal acceleration. So where are we now? We've realized that there is centripetal acceleration. There's acceleration when something moves in a circle. Now we're going to find out the direction of the acceleration. And we're going to find out the size of the acceleration. So that's the goal of this slide and the next slide. Let's take a look at that. Okay, so let's take a look at this picture. So here I'm imagining some object. It's in this yellow color here. That is moving in a circular path around some axis. And what I've actually done on the sketch is I've pictured the object at one moment, here it is on the left, and then another moment, a little later, here it is on the right. And I pictured the object at those two different moments in its circular path, and I pictured its velocity vectors at those two moments. Those velocity vectors are tangent to the circle, and they have some interesting features to them. So they're going to have the same length because this is uniform circular motion, but the direction has changed. The tangent to the circle over here on the left, the initial moment that I pictured the velocity vector, that's mostly towards the right, but a little bit up. The velocity vector over here on the right, which is a little bit later, that velocity is still mostly towards the right, but now it's a little bit down. And so there you see again that the velocity vector is changing, even in uniform circular motion, which means that there must be acceleration in uniform circular motion. And what I want to do is figure out in what direction is that change in velocity, because in whatever direction that change in velocity is, that's the direction of the acceleration. So we're going to do that. And that's what this diagram will help us with. I've taken this initial velocity vector that I drew. Over here. And I've drawn it, expanded it, over here on the right. I've taken this final velocity vector that I drew. And again, I've expanded it and drawn it over here on the right. And once again, the sizes of these velocity vectors before and after are the same. Their directions are just a little different. They're both going towards the right, but one was going up and one was coming down. So those velocity vectors are a little different. And here is the difference. This thing I call delta V, this velocity I call delta V, is how you turn the initial velocity into the final velocity. It's what I have to add to the initial velocity to make the final velocity. And so that's the change in velocity. And you notice that that change in velocity, we said that both before and after, there was a large component of velocity from the left to the right. That hasn't changed. What's changed is that before and after, there was a small component of velocity upwards, and then after, there's a small component downwards. That's the change. And the change is going from up to down. And so that change velocity vector, delta V, is a downwards velocity vector. And so you can see it here in this velocity vector addition triangle, and I've drawn it over here. It's towards the axis of rotation. And that's the answer to the question about what's the direction. The direction of the velocity change, as we've just sketched out, is towards the axis of rotation. So that's a big discovery. And the centripetal acceleration, therefore, is towards the axis of rotation. And no matter where I drew this initial and final velocity, maybe I'd have drawn them at the bottom of the circle, or over here on the left of the circle, or over here on the right of the circle, we would have reached exactly the same conclusion. You could try this out for yourself. You would always find that the change in velocity is pointing towards the center of the circle, that the acceleration, centripetal acceleration, is towards the center of the circle. So that's a huge discovery that we've just made. So that's actually really, really great. Okay, so that's the direction. Now let me move on to the next slide, and let's look at the magnitude of the centripetal acceleration. How big is it? Well, you might guess right. You know, you've got big circles, small circles. You've got fast-moving, circling things, slow-moving, circling things. It will depend on the size of the circle, radius of the circle, and depend on the size of the velocity, magnitude of the velocity. That all makes sense to me. So let's see if we can trace out that. Firstly, I was kind of interested in how does it depend on velocity? And this little diagram is meant to show you that. So how's it going to depend on the velocity? So what I did was, I just cut and paste this little diagram from the last slide. Upstairs here is that initial velocity. Downstairs is this final velocity. And here's the change in velocity. So we can see the change in velocity on this picture as the object went around the circular path. Now I'm going to make it go around twice as fast. If I make it go around twice as fast, I've got to firstly, I've got to double the length of these velocity vectors. So I did that. If you look, this initial velocity, this final velocity is twice the length of the initial and final velocities over here on the left. But I did one more thing. If it's going twice as fast, it's going to get twice as far around the circle. And so I've got to double this angle from this corner to this corner, because it's going to go a greater angular distance around the circle. And so I did those two things. And I end up with, when I drew it pretty carefully. Here's the change in velocity now. It's a lot bigger. And actually, if you double the velocity, it makes the change in velocity, the acceleration, 4 times bigger. And it's doing it for these two reasons. You're making the velocity twice as big, so you got change as bigger, twice as big a velocity, but you're also making the angle that it covers twice as big. And so it's turned twice as much. The direction has changed twice as much. And so you get two factors. And that's why it's 4 times, the change in velocity is 4 times bigger when you double the velocity, or the centripetal acceleration is 4 times bigger when you double the velocity. Okay, second question is, what about r? That's the radius of the circle. What happens if I change the radius of the circle? Well, if I change the radius of the circle, let me double the radius of the circle. So over here, on the left, I'm imagining, again, something, say the Earth around the sun, moving around the sun, Earth moving around the sun with constant speed. And I imagine it at one moment and another moment later, initial velocity, final velocity. And here's the change. Here's the change in velocity that acts towards the center of the circle, the axis of rotation. Now let me double the radius. If I double the radius of the circle, well, the velocity vector's lengths don't change, still going around the circle at the same speed. What does change, though, is that the amount of direction change. If I double the radius of the circle, the direction change will halve, because now I've got a circle that's bigger. As I go around that bigger circle, I'm changing my direction less quickly. And so now these two velocity vectors before and after are the same length as they were over here on the left, but the difference in their directions is smaller. And so the resulting change in velocity is smaller. And again, if you draw it carefully, if you double the radius of the circle, you actually halve the change in velocity. Well, this slide has answered 2 questions that we suspected. We suspected centripetal acceleration would depend on the velocity and the radius of the circular motion. Now we know how it depends on the radius and the velocity of the circular motion. And we can summarize that in a little equation. Here it is, that the centripetal acceleration's size is in proportion to the square of the velocity divided by the radius. So if you double the velocity, you quadruple the centripetal acceleration. If you double the radius, you halve the centripetal acceleration. And that's simply because by increasing the velocity, you both have to change a larger velocity vector and change its direction faster. That's why that goes as v squared. And if you increase the radius, it means you change the direction slower, which means it goes, as the acceleration goes, as 1 over the radius. If you like, I'm not going to do this here. Oh, I didn't mean to do that. Let me go back. We derived an equation here. You can check its units are right if you like. So if you want to check its units are correct, I keep doing this. Just fill in the units of velocity over here on the right-hand side, the units of length of radius, length over here on the right-hand side, and check they're equal to the units of acceleration. And indeed they are if you do that exercise. And we could even have kind of derived that equation from dimensional analysis. Okay, I want to demonstrate centripetal acceleration. And I'm going to show you a little movie, but I want to show you the device that I'm using to measure acceleration. This device in the picture on the right here, this is called an accelerometer. So this guy here is an accelerometer. And I made this one at home. I made it at home last night. Spent the whole evening doing this, sadly. And the way I made it was I got an old, I think it was Diet Sprite, 2-liter bottle of Diet Sprite. So I drank the 2-liter bottle of Diet Sprite. I got the bottle, empty bottle. Then I needed a cork. So I had to get a bottle of wine. So I had to drink the bottle of wine. I've got a cork. I tied the cork on a string. I filled the Sprite bottle up with water. I put the cork in the water. I put the top back on and trapped the string in the top. And I built myself an accelerometer. So the thing about the accelerometer is, you know, here's the container, the water. Here's the cork inside the water. And here's the string. That if I was to accelerate this towards the right, the cork, which has lower density than the water, would move towards the right. If I was to accelerate this towards the left, the cork, which has lower density than the water, would move towards the left. And so I would really, you know, if you've got nothing to do tonight, you could build one of these accelerometers and you can try it out. Just start moving it around, shaking it left and right. You'll see that it measures acceleration. It's a device for measuring acceleration. The cork points in the direction of acceleration. And so I'm going to use this to demonstrate acceleration in circular motion now. So I want to share a different screen. If I'm capable. Here we are. And so what I hope you can see now is I've actually got 2 accelerometers. I built more of them. It was so enjoyable. And I built these 2, they're identical ones, and I've mounted them on this rotating arm. And we're going to measure the acceleration when this device rotates. And we're going to see the centripetal acceleration. So what I'm going to do is set this in motion. And here I'm just pointing out there is a string there, and that's the cork attached to it. So it is an accelerometer, like I showed you in the photograph of the one I made last night. And so there's one over there on the right-hand side, and then there's one over here on the left-hand side. Again, I'll point out the little string. You can just see it there, and the cork. And that too is an accelerometer. And those corks are going to point in the direction of any acceleration. Now, right now they're just standing straight up, like little soldiers. That's because there is no acceleration. But if we set this arrangement contraption in motion, we're going to see the direction of the acceleration. So that's what I'm doing here. Look, you see those corks pointing inwards towards the axis of rotation. You're seeing with those corks the centripetal acceleration. So that's a big discovery. This was a big discovery in physics. It goes back to Newton's time, to realize that hidden within circular motion that looks so kind of constant and uniform and repetitive is an acceleration. And that acceleration is towards the center of the circle, and it depends on the velocity, and it depends on the radius. And you see as it slows down, the corks straighten up. As it slows down, v is decreasing, v squared is decreasing a lot. And so the centripetal acceleration is decreasing a lot. Okay, let me go back to my slides, if I can do that. And I want to do a couple of quick calculations of centripetal acceleration because we now we've met it. First one I want to calculate is the centripetal acceleration of the moon in its orbit around the Earth. And so that's what I'm doing in this top half of this slide. And then we're going to do calculation of the centripetal acceleration of the Earth around the sun. And I'll do that in the bottom half. So these are, you know, if you ask somebody what is the most obvious circular motions that naturally occurring, you might say the Earth's motion around the sun and the moon's motion around the Earth. And here we are, we're going to calculate the most basic thing about that, those circular motions, their accelerations, their centripetal accelerations. And we're going to do it based on some astronomical data, we would call it. So we actually, since ancient times, we knew estimates of the period of the moon around the Earth and the Earth around the sun, and we also knew the distance from the Earth to the moon, that would be the radius of the moon's orbit, and the distance from the Earth to the sun, that would be the radius of the Earth's orbit. So we know those things. And for the moon, I've written them down here. I've got to get my pen going again. Here's the radius of the moon's orbit in kilometers. And here's the period of the moon's orbit in kilometers. So moon's radius is about, of its orbit, is about 0.4 million kilometers. And the period, as you know, is about a month, it's 27 days. Now, to calculate the centripetal acceleration, I need the velocity, and I need the radius of the orbital motion. I know the radius, but I don't immediately know the velocity, but I can calculate that. So that was actually a first step that I did here. What's the velocity of the moon? Well, it's the distance it travels, the circumference of the circle, multiplied by the period. And that comes out to be 1,000 meters per second. So this is just velocity equals distance over time. And I'm just applying it to one lap around the moon's orbit. Now I've got the velocity, I can actually calculate the acceleration, the centripetal acceleration. I've just got to square up the moon's velocity, divide it by the moon's radius. That's what I've done here. And I get this little number here. So 0.0027 meters per second squared is nothing compared with the acceleration of gravity. You'll notice that. And so that's our answer for the moon's orbit. And I was a little careful here. I did have to, look, I hit a little bit of work. The radius of the moon's orbit I was given in kilometers. I had to put it into meters. The period of the moon's orbit I was given in days. I've had to put it into seconds. But I did all that. And we come up with this roughly 0.003 meters per second squared. Let's do the second example, which is the Earth going around the sun. So again, here also, we do know the radius of the Earth's orbit around the sun. Here it is. This is 150 million kilometers. So the moon, the Earth, as you know, is much, much, much further from the sun than the moon is from the Earth. And then here's the period. And of course, this is 1 year, or 365 and a quarter days. Again, we're faced with this problem that to calculate the acceleration, the centripetal acceleration of the Earth, we need the radius, which we've been told directly, and we need the velocity, which we're going to have to calculate. This is the radius of the Earth's orbit. This is the period of the Earth's orbit. Anyway, so I first calculate, like I did upstairs here. I'm going to first calculate the Earth's velocity by taking the distance it travels and divided by the elapsed time and considering one complete orbit. So here's the circumference of one orbit. Here's the time to go around one orbit. If I divide one by the other, I get the Earth's velocity around the sun. It's 30,000 meters per second. So, you know, compared to everyday velocities, right? Both the moon around the Earth and the Earth around the sun, they're moving fast. And the Earth is moving much faster than the moon here. Okay, now we know both the velocity of the Earth, the radius of the Earth's orbit, and I can feed them into our equation for the centripetal acceleration, and I come up with an answer. Here it is 0.006 meters per second squared. And I actually always think this is kind of interesting. I mean, it's not a conspiracy or anything like that, but it's kind of interesting, intriguing that, you know, these circular motions of the moon around the Earth and the, what's the other one? Earth around the sun, they're very different scales. You know, one was, you know, several hundred times larger distance scales. And they're different time scales too. One's more than 10 times longer. But when we calculate the accelerations, the centripetal accelerations, they're not so different. One's 0.003 meters per second squared, one's 0.006 meters per second squared. Again, in both calculations, I did have to do this unit conversion that I didn't really show on this slide. Okay, so that's an illustration of using the expression that we figured out for the centripetal acceleration. Let's go on to the next slide. Okay, so in this slide, I've got just a few pictures of circular motion. This car going around a mini roundabout up here, this roller coaster going around a track here, this child on a swing, that's a fraction of a circle that child is moving in. And I want to make a really important point. So it's a really important point. It's a really key point. You know, again, it was Isaac Newton and some of his colleagues that firstly realized that there's acceleration in circular motion, and realized if there's acceleration in circular motion, it implies there must be a force to execute circular motion. And so the recognition on this slide, this really important slide. I wish Lady Gaga could have been here for this one. She would have recognized, look, you've got centripetal acceleration. To have that centripetal acceleration, there must be some sort of centripetal force beneath that is creating that acceleration. That's the recognition here. And I've written down a formula to go with that. Based on Newton's second law, here we are, Newton's second law. If you see an acceleration, there must be a force acting, because forces cause acceleration. Forces are creators of acceleration. If we see our centripetal acceleration associated with circular motion, there must be a corresponding centripetal force that's associated, creating that circular motion. And since we know the equation for centripetal acceleration, that tells us the equation for centripetal force. It's the mass of the circling object multiplied by the square of the speed at which it circles and divided by the radius in which it circles. And so that's a big breakthrough. Oh, I was trying to show you the little, on this picture, I forgot all about that. I did that. It took me an unusually long amount of time. I tried to draw the force vectors in each case. So here the car is going clockwise around the mini roundabout. There will be a centripetal force towards the center of the roundabout. Here the roller coaster is going around the roller coaster track. There will be a centripetal force towards the center of that circular motion. And the child on the swing is executing at least a portion of, only a portion, I hope, of the circular path, and there will be a force towards that axis of rotation. And so now we're able to see not just the centripetal acceleration in these circular motions, but we're able to see the centripetal forces themselves. I want to show you a demonstration. I'm going to show you one of these two. They're both in the modules directory, so you can look at the other one. I'm going to share a different screen. So, you know, it'll only take me 10 minutes or whatever. Here we are. So I shot this in black and white for effect. I'm not going through my black and white period. And what you see is a steel ring and a meter stick. So the steel ring is on the right, and the meter stick's on the left. The steel ring, you notice, has a gap in it, and so its shape is a circle, and then next to it is a meter stick, and its shape is a straight line. And we're going to see both of these types of motion, circular motion, straight line motion, in the little demonstration I got for you. I really like this one. So I'm going to get a little steel ball. Here you can see it. And I'm going to get that undergoing circular motion around the steel ring. And I'm going to use this to demonstrate the existence of the centripetal force. So here goes the steel ball, executing a circle, but then there's a gap, and it just goes in a straight line. What does that tell us? That's a beautiful example of centripetal force. As it goes around the circular path inside the ring is pushing on the steel ball to make it go in that circular path. It's exerting a centripetal force to give it the centripetal acceleration to go in the circular path. As soon as the ring vanishes and it can no longer push on the ball, then the ball no longer experiences the centripetal force. The ball no longer experiences centripetal acceleration, and therefore it's not accelerating, it's going to go in a straight path at the same constant speed. And so you're seeing here, circular motion needs a centripetal force, centripetal acceleration, straight line motion. Straight line motion at constant speed has no net force and no acceleration. Okay. Let's go back to the lecture slides. And I've got a quiz. Okay, so the answer to this one is that the centripetal force is 2 times larger for tennis ball A compared to tennis ball B. What's happening there is that, firstly, tennis ball A is at twice the radius. So that would make, alone, that would make the force half as big. But tennis ball A must also be traveling twice as fast in meters per second to get around the circle in the same time as B. So it's going twice as fast, which means that from the velocity alone, that would make it 4 times, the centripetal force 4 times bigger. So the velocity is doubled, the radius is doubled. The velocity doubling makes the force 4 times bigger. The radius doubling makes the force half as big. The combination of those is that you need twice as big centripetal force for A to go around the circle as B compared to B going around the circle. Okay, let's look at a question, a problem or two, a numerical problem or two, and these last 15 minutes. And so this one is all movies today. It's Tarzan. We're told that 110 kilogram Tarzan swings on a 30-meter long vine. If the vine will snap, break, for a tension of 2,100 newtons, what's Tarzan's maximum speed? And we're going to solve this problem by understanding centripetal forces. And we're going to understand in this problem the causes of look more carefully at the causes of the centripetal force as Tarzan swings on the vine. So the first thing I'll do with all these problems is, of course, make a sketch of the forces that are acting and the resulting net force and how it creates a centripetal force. And so that's what I'm doing here. And so in this picture, let me get my pen going again. So here's Tarzan, spherical Tarzan. In black here, here's the vine that he's swinging on. And over here from the left to the right, this is his swinging motion. And there are two distinct forces that are acting on Tarzan. One's Tarzan's weight. He's 110 kilograms. That's kind of a heavy Tarzan, I think. But it's 110 kilograms, and so he has a corresponding weight that's 110 kilograms times 9.8 meters per second squared. And then there's he's hanging on the vine, there's the tension in the vine. And so that there's a tension in the vine here. And so I've drawn two force vectors, if you can see the weight in blue, the tension in this magenta-like color. Now, if Tarzan was just hanging from the vine, those two forces would be equal and opposite one another. The vine would simply be supporting Tarzan against the pull of gravity. But Tarzan's not just hanging on the vine. Tarzan's swinging from left to right on the vine. And so he's executing at least part of a circular motion. He's executing an arc of a circular motion. And so to go in that circular path, to go in that circular arc, there must be a centripetal force. There must be a centripetal acceleration. So these two forces in this case for swinging Tarzan compared to at-rest Tarzan, for swinging Tarzan, those forces aren't equal and opposite, but rather they add up to make a net force. Here's the net force, the sum of the individual forces that provides the centripetal force. And so this is kind of the picture of what's going on here in terms of forces. There's individual force, tension, and weight that combine together to make a net force. My phone's going off. And combine together and make a net force and a centripetal force. And so that's the basic idea for solving this problem. Here's the key thing, that there is a centripetal force on Tarzan. It is the net force on Tarzan that is due to the combination of the upwards tension force and the downwards weight, force of gravity. And so that's the key ingredients, the key components in solving this problem, in ultimately finding this speed. Okay. Okay, so on this slide, I just redrew the sketch so we have it to consult if we need it, I guess. Here's the sketch from the last slide. And here's kind of how we ended the last slide, that the centripetal force is due to the combination of tension and weight. And now I'm going to start thinking about the maximum centripetal force that corresponds to the maximum speed that corresponds to the maximum tension. And I'm going to try and find this maximum speed. What is this maximum speed? that if Tarzan swings faster than that, that vine is going to break. He's going to get hurt. If he swings slower than that, then Tarzan's safe. He's not going to get hurt. The way to do that is I'm just going to fill in that equation for the centripetal acceleration. I filled it in over here, and I've equated it with this sum of tension and weight. And if you look at this equation here, it contains in it the speed that we want, the maximum speed of Tarzan, and all the other things. Tarzan's 110 kilogram mass, the tension, the maximum tension, 2,100 newtons. The radius of the circle, which is the length of the vine. We know them all. I can just rearrange now, multiply by r, divide by m, take the square root, and get an equation for this maximum speed here in terms of these quantities I know over here, and I can start feeding in the numbers. And that's what I did was the last step. I fed in the radius of the vine, the maximum tension in the vine, Tarzan's 110 kilograms, and 9.8 meters per second squared for the acceleration of gravity. And out of that comes a calculation of the maximum velocity. Well, didn't mean to do that either. Now I've got to go back. Here we are. Here's the maximum velocity, maximum speed. And here it is. It comes out to be about 17 meters per second. So that's an example. You know, it's quite a sophisticated problem in terms of reasoning what's happening in terms of forces like weight and tension, the net force and centripetal force. The calculation itself wasn't too difficult. Didn't involve many steps, but the reasoning, the key reasoning is that now we're able to recognize within circular motion, there is acceleration. Within circular motion, there must be a force that causes the acceleration. And with that interpretation, we are able to link that force associated with the circular motion to the individual forces that were acting on Tarzan. That's how we worked our way. That's how we walked our way through that problem. I'm going to show you one more example. Okay, so here I'm at Kings Island, I guess. Actually haven't been there for a while. But, roller coaster loops the loop in a 25-meter radius circle at a speed of 22 meters per second. So that first paragraph, right, they're telling us the radius of a circular motion and the speed of a circular motion. They're telling us the ingredients in a centripetal acceleration. In the next paragraphs, they tell us the roller coaster has a mass of 9,000 kilograms. So they've also told us all the ingredients that's in centripetal force. And they ask us to find the normal force of the track on the coaster at the bottom of the loop and the top of the loop. So let's think about that question a little bit. Imagine that the coaster's upstairs here. The track is actually pushing on the coaster, and we'll find it's pushing on the coaster towards the axis of rotation, the center of the circle. And we want to find that normal force. Likewise, at the bottom of the circular motion, downstairs here, the track is also pushing on the roller coaster towards the center of the circle. And we want to find that normal force. And we're going to find these two normal forces by understanding that to go around the circular path needs a centripetal force. And by thinking about what forces are actually providing the centripetal force. And it is actually a combination of these normal forces from the track and the force of gravity from the earth. And so that's our route through this problem. That's our sort of guidebook through this problem. So let's go ahead and do that. And so there's two slides here for the top, the roller coaster at the top of the loop, and the roller coaster at the bottom of the loop. And there could be two calculations with these two slides. So that's what we're going to do. And this one's, oh, This one is at the top. So here we are, the roller coaster, here it is at the top of the loop. And before I try and calculate the normal force of the track on the roller coaster at the top, the key thing is to draw these forces that are acting and see how they're related to the centripetal force. So when the roller coaster is at the top, there are two forces acting on it. One is the pull of gravity. One is the normal force of the track on the roller coaster. And they're both pushing downwards. So gravity always pulls downwards, of course, because the Earth's beneath the track. But the track is also pushing downwards in this case because the track is above the roller coaster. And so here's the force of gravity, I drew it in blue. Here's the normal force, I drew it in green. And these two downward forces, when we're at the top of the roller coaster, they're going to add together. They're going to make a net force, the sum of the forces, the total force, which is going to be the centripetal force that's needed to go around the circular path. And so that's the key understanding of what's going on in this problem. And I can use that picture, that understanding, that comprehension of the forces, centripetal, net, weight, normal, to solve for the normal force. And so let me then do that. And this is my calculation. So the first thing that I wrote down is this link here. Oh, hold on, I've jumped ahead too many slides. This problem's going from bad to worse. Okay, here we are, still on the top. I wrote down here this key equation that's describing how it is that the centripetal force is provided by the net force on the roller coaster, and that net force is due to normal force and the weight. And in this case, both of those act towards the center of the circle. And I've called that direction towards the center of the circle the positive direction. And now I'm going to fill in or solve this for the normal force. So firstly, I rearranged this equation for the normal force. The normal force would be the difference between the centripetal force and the weight. That's here. Here's the centripetal force. Here's the weight. And then I wrote the centripetal force in terms of the speed, the radius, and the mass of the car. I wrote the weight in terms of the acceleration of gravity and the mass of the car. All of these quantities I know. And so I was able just to stick their values in. I did that here. And after doing the calculation, here's the normal force. The other calculation, the second calculation, was to do exactly the same computation for the normal force, but now when the cart is at the bottom. So let me just show you this quickly and then I'll end. I again drew a picture. I drew a picture now of the roller coaster at the bottom of the track. And I added to that picture the forces that are acting on the roller coaster. So again, there's weight acting downwards in blue here. Now the normal force has reversed its direction though, because now the track is not above the roller coaster, it's below the roller coaster. So it is pushing upwards on the roller coaster. And in green here, here's the normal force. Again, these two forces will add together, except they're oppositely directed, to make a net force. Here's the net force, and that net force will produce the centripetal force. So that's the understanding of what's going on. You need a centripetal centripetal force, it's due to the net force. It's going to be made by this combination of weight and normal force. We can turn that into an equation, right? That's what I've done over here on the right. The centripetal force is the sum of the forces, the net force, and those net forces are a upward normal force that acts towards the center of the circle, the axis of rotation, and a downwards now gravitational force that acts away opposite the direction of the axis of rotation. We want to solve for n. So I can rearrange this equation for n. N is Fc, the centripetal force, less the weight, mg. And so if I rearrange this equation here, I get that the normal force is equal to the centripetal force plus the weight, this guy here. If I put in the centripetal force in terms of the speed and the radius of the circle, put in the weight in terms of the acceleration of gravity, I get this little equation here. I know all these quantities. I can feed them in, and I figure out the normal force. And so that's the case at the bottom of the incline. Just to end with, just comparing those two, at the top of the incline, we needed less of a normal force. Bottom of the incline, we needed more of a normal force to maintain the circular motion. The reason we need less at the top is because the normal force and the weight act in the same direction. They work together to provide the centripetal force. The reason you need more at the bottom is because the normal force and the weight act against each other in trying to provide the centripetal force. The normal force has to overcome the weight. It's in the wrong direction for the centripetal force, and so it has to be much bigger. Anyway, that was a second example of our understanding of circular motion. Next class, sorry I've overrun a minute or two here. Next class, we're going to use what we've learned about circular motion and introduce universal gravity.